This webcast is the first in a discussion of Newton's second law. And so we're in worksheet 5B. The first problem concerns an elevator, and it tells us that the elevator is moving upward at a constant velocity of 2.5 meters per second. And it gives us the mass of the passenger. Okay, so we are first going to make a force diagram for the passenger. And so I'm trying to draw something for just the passenger, right? Okay, so let me set up my coordinate axes. There's my vertical one, here's my horizontal one. The box in the middle, this represents the passenger, and I'm trying to show all of the external forces acting on the passenger. Well, a good place to start is the gravitational force, which is the same thing as the passenger's weight. And so I'm going to show that that is a force that points down toward the center of the earth. It's the gravitational force that's being exerted on the passenger, and the object that's exerting this force is the earth. We need to figure out the amount of this, so they've given me the mass of the passenger, and the weight, or the gravitational force, always equals the mass multiplied by the acceleration due to gravity. So in this case, that's 85 kilograms multiplied by 9.8 meters per second squared. And so that's 833 newtons. Okay. The passenger is sitting or standing on the floor. They're not falling through the floor. And so therefore I know that there's a force pushing the passenger up. And that type of force is a normal force. It's being exerted on the passenger, and it's being exerted by the floor of the elevator. Now, can I figure out how much that is? They told me how the elevator is moving. It's moving at a constant velocity. And so therefore, because of the balanced force model, Newton's first law, I know that when something is moving at a constant velocity, the net force, the sum of the forces acting on him, equals 0. If that's true, then there has to be as much force pushing the passenger up as there is pulling it down. And so these two forces, in this case, are equal. And so I can say the normal force on the passenger is also 833 newtons. Remember, I only know this because the elevator is moving at a constant velocity. Okay. B says calculate the force that the floor exerts on the passenger. That's the normal force. And since in this case, if I took the sum of the forces in the direction of motion, that's the vertical direction, I know that that sum of the forces, I add the force that points up, that's the normal force, I subtract the force that points down, that's the gravitational force, and the sum of these forces has to equal 0 since the elevator is moving at a constant velocity. Therefore, I know that the normal force equals the gravitational force, which equals 833 newtons. Okay, let's go on. We're still in this elevator, but now it's telling us that the elevator is accelerating upward at 2 meters per second squared. Okay, so it's no longer true that it's moving at a constant velocity. And so now, my force diagram is very similar, right? The gravitational force is still the same, right? The passenger still weighs the same amount. So that's 833 newtons. And there is still a normal force supporting the passenger, and that pushes the passenger up. But I no longer know that the net force is 0, and therefore these two forces are no longer equal. Since the acceleration is upward at 2 meters per second squared, I believe that the net force is also upward, right? Because acceleration and net force are always in the same direction. That means that the normal force in this case should be greater than the gravitational force, but we're going to figure out how much it is. Okay, so in these types of problems where the net force is not 0, the strategy is this. First, you're going to write two different equations to find the net force. One of them is going to be Newton's second law, that tells us net force equals mass times acceleration. The other is going to be the equation to find the net force in the direction parallel to motion. Okay, that equation might be a little different depending on the situation, right? And then you're going to set those equations equal to each other and solve for the variable that you're trying to find. Let's see how that works. So first, it says write an equation for the vertical forces on the passenger. So that's the sum of the forces in the vertical direction. And so I add the force that points up, and then I subtract the force that points down. In this case, the sum of these forces is not 0, and I know that because the thing is accelerating, okay? So I know that the net force is not 0, okay? So that's one of the equations to find the net force. But now I'm going to write the other equation, which is Newton's second law. Net force equals the mass times the acceleration. In the first part of this problem, they told me the mass of the passenger. It's 85 kilograms. And just here in number 2, they're giving me the acceleration. It's 2 meters per second squared. And so therefore the net force on this passenger when he's accelerating is 170 newtons. Okay, so now I've got my two equations, and what I'm looking for is the force that the floor exerts on the passenger. So I'm looking for the normal force on the passenger by the floor, right? That's the force that I'm looking for here. That's what this means. Okay, so I set these two equations equal to each other, right? I know that the net force equals the normal force minus the gravitational force, but I also know that it equals ma, and I'm looking for the normal force, right? So the normal force is going to be the weight. I'm going to add Fg to both sides, basically, right? So it's going to be the gravitational force plus the mass times acceleration, which is 833 newtons, right? We calculated that in the first part of this problem, and I'm going to add the net force, which is 170 newtons. And so in this particular situation, the normal force is 1003 newtons. Okay, so just reviewing, I wrote two different equations for the to find net force. First, I used the force diagram to find the net force in the direction of motion. That's the net force in the vertical direction because the elevator is moving up and down. And then I used Newton's second law to write an equation for the net force. Net force is mass times acceleration. And then I set those two equations equal to each other. And I solved for the variable that I was looking for. Okay, let's go on. And let's look at number 3 here. So here, we're still in an elevator. But now as the elevator approaches the top of the building, it accelerates downward at 3 meters per second squared. That means that the acceleration is pointing down, and so it equals negative 3 meters per second squared. Okay? So it says, let's make a force diagram. Okay. So, you know, all these force diagrams, they look the same, right? We've got the same two forces, since we're talking about the same elevator, and the same passenger. So the weight of the passenger, that's the gravitational force on the passenger being exerted by the Earth. We've already calculated that. That's 833 newtons. Okay. And then the floor is supporting the passenger. The floor that he's standing on is supporting him with a normal force. I know that these two forces are not equal to each other because this is a situation where the passenger is accelerating. And since he's accelerating downward, I know that the net force is also pointing downward. In other words, that means that there must be more force pulling him down than there is pulling him up. So in this case, the gravitational force must be greater than the normal force. I know that, but we're going to go and calculate what the normal force is. Okay, so my strategy is to write two equations to calculate the net force. Okay, so my first equation is going to be based on my force diagram. The net force in the vertical direction, that's the direction that the passenger's moving, equals the normal force minus the gravitational force. This net force is not zero because the passenger is accelerating. Okay, and then I'm going to write another equation to find the net force. And in this case, I'm going to use Newton's second law, which says net force equals the mass multiplied by the acceleration. I happen to know both the mass and the acceleration in this case, so I'm going to go ahead and calculate that. The passenger has a mass of 85 kilograms, and now, in number 3, his acceleration is negative 3 meters per second squared. And so the net force is negative 255 newtons. What does that negative mean here? It means that there's more force down than there is up on the passenger. Okay? Or in other words, the gravitational force is bigger than the normal force by that 255 newtons. So now I'm going to set these two equations equal to each other. Okay, so the net force equals the normal force minus the gravitational force, and it equals MA, which we just calculated to be negative 255 newtons. Okay, I'm solving here for the force that the floor exerts on the passenger, which is the normal force. So the normal force equals Fg plus MA, and so it equals 833 plus that negative 255, and so that's going to equal 578 newtons. Okay? Okay. Number 4 says, while the elevator is descending, the cable breaks. And so now there's nothing holding the elevator car up. So how big is the force on the passenger by the floor? Well, in this case, there is no normal force. You know, both the elevator and the passenger are now in free fall. And since the elevator is in free fall, there's nothing, it's no longer able to support the passenger. Okay? Okay, that's one of those hokey physics problems. That's not exactly how an elevator works. But if the box and the passenger were both falling, the box would not be able to support the passenger, so there'd be no normal force. Okay, let's look at number 5. So here we have a skydiver jumping out of a plane. Okay, so first we're looking immediately after jumping. The significance of that is, you know, when they first stepped out of the plane, the skydiver is in free fall. In other words, they have not started they have not sped up to the point that drag force is significant. And so therefore, the net force is the force of gravity. Okay? And so therefore, the acceleration is going to be negative 9.8 meters per second squared. That's what happens when something is in free fall. But after a little bit of time passes, the passenger is now, they have sped up to the point that they are now moving at 100 miles per hour. And the significance of that is now drag force is bigger. It's not negligible anymore. So now we have to consider the drag force. So let's do a force diagram for the skydiver. So a good place to start is always the gravitational force, which always points down to the center of the Earth. That's a force exerted on the skydiver by the Earth. And we can calculate that by multiplying the mass of 70 kilograms by the Earth's acceleration due to gravity. Which is 600, and so that gives us a weight of 686 newtons. There is no normal force here, right? The skydiver is falling, so there's nothing supporting their weight. But because the skydiver's speed has gotten so fast, they are hitting air molecules very quickly, and each of those molecules is pushing the skydiver up a little bit, and so there is now a significant drag force. So there's a drag force on the skydiver by the air, and I don't know what that is yet, but I know that these two things are not equal because I do know they've told me the air resistance causes 300 newtons of drag force. Okay, so they've told me this. So now they're asking me, what is the acceleration? Okay, I'm still going to use my strategy, which is to write two equations to find the net force, and then I'm going to set those equations equal to each other and solve for the variable that I'm trying to find. Okay, here though, I'm not trying to find a normal force, I'm trying to find the acceleration. Okay, so the first equation, I can use Newton's second law the net force equals the mass times the acceleration. And I know the mass here, but I do not know yet the acceleration. My second equation to find net force is going to be the net force in the direction of motion. Here that's the vertical direction. And that's going to be, I add the force that pulls the skydiver up. So I add the drag force, and then I subtract the force that points down. That's the gravitational force. So now I set number 1 equal to number 2, right? So I have that net force. Oh, I meant to use blue for that. Net force equals the mass times the acceleration, but it also equals the drag force minus the gravitational force. The variable that I'm solving for is the acceleration. So the acceleration would be the drag force minus the gravitational force divided by the mass, right? I've just divided both sides of this equation by mass, and so I get 300 minus 686. I'm plugging in all the values that I know, divided by 70. That was the mass of the skydiver that they gave me. Okay, so the skydiver is accelerating at negative 5.514 meters per second squared. The acceleration is negative because the skydiver is speeding up as they move in the negative direction. Okay. So in number 6, they're talking about an elevator again, and it's initially at rest on the ground floor. They're giving me the acceleration at different points of time. So as it moves upward, it accelerates upward at 2.4 meters per second squared. Then in the middle, it moves at a constant velocity again. And then as it's getting up toward the top of the building, it accelerates down. It's really accelerating downward, sorry, at negative 3.5 meters per second squared. And at the end, it's at rest on the 16th floor. Okay, so the question here is, what would be the scale reading at each of these points? Well, the way that a scale works, the scale reading is telling you the amount of the normal force on the man being exerted by the floor, or by the, by the floor or by the scale, okay? And so, let's see. When the man is not moving, and that's situations A and E, the scale reading, the normal force, equals the man's weight, which equals the 90 kilograms times 9.8. Right, that's his weight. Which is 882 newtons, okay? That's what the scale will read at A and E, okay? When the man moves at a constant speed, and that's like part C. By the way, this is an E, and this is a C. Well, once again, the normal force equals the gravitational force, which equals 882, right? Because, both of these two situations are where the net force is 0. But for B and D, we will have to actually calculate, okay? So for part B, we know that the acceleration is 2.4 meters per second squared. So I'm going to write two equations to find the net force, right? First, I've got net force equals mass times acceleration. And I think I can calculate that, right? It's 90 kilograms times 2.4. which is 216 newtons. But I also know that the net force in this situation is the normal force exerted on the man by the floor minus the gravitational force. So I set 1 equal to 2. I'm going to solve for what I'm looking for. So I've got the net force equals 216 newtons. But it also equals the normal force minus the gravitational force. In this case, I'm looking for that normal force because the normal force equals the reading on the scale. And so therefore, the normal force equals the 216 plus the gravitational force, which is 216 plus 882. Which is 1098 newtons. Okay, so at A, the scale was reading 882 newtons. At B, it's reading 1098. Then in the middle, it goes back to 882. And at the end, it's at 882. But let's see what it is at D. So for part D, again, I need to write two equations to find the net force, and then I'm going to set number 1 equal to number 2. Okay, so first I have that the net force equals the mass times acceleration, and I can calculate that because they gave me the acceleration, right? The acceleration is negative 3.5. So I have 90 times negative 3.5 is negative 315 newtons. But I also know that the net force, looking at the force diagram, would be the normal force minus the gravitational force. I set these two equations equal because they both equal net force. So net force equals MA, but it also equals normal force minus gravitational force. I'm looking for the normal force. So the normal force equals MA plus FG. So it equals negative 315 newtons plus 882 newtons, which would be 567 newtons. And so that's what the scale would read as in part D, where the elevator is accelerating upward at negative 3.5 Newton, negative 3.5 meters per second squared. Okay, and we'll do one more, number 7. Again, this is an elevator. James is in the elevator. And here, instead of giving us the acceleration, they're going to tell us what the scale is reading. In other words, they're giving us the normal forces. So when he's at rest, his weight is 934 newtons. This is his true weight. Okay? Okay. As the elevator rises, the scale reading increases to 1100 newtons and then returns to normal. And then as the elevator slows to a stop, as he gets to the 10th floor, the scale reading drops to 688 newtons. Okay? So, the acceleration when the scale reads 1100 newtons. Okay, I have to write two equations to find the net force, and then I need to set those two equations equal to each other. One of the equations is Newton's second law. Net force equals mass times acceleration. One of the equations is based on the force diagram for someone sitting in an elevator, and we've done this many times now. That equals the normal force exerted on James by the floor minus the gravitational force exerted on James by the earth. I set these two things equal to each other because they both equal net force. And so I'm going to be solving for the acceleration. Okay, so there's one thing to think about here. What is James' mass? They haven't told me that. So his weight, his true weight is 934 newtons, and that equals his mass times 9.8. So his mass is going to be 934 divided by 9.8, which is 95.3 kilograms. Okay, so now I know his mass. I know the normal force because it tells me that. I know the weight because it told me that. So 95.3 times the acceleration equals the normal force. It said it was 1100 newtons as it was going up, minus his actual weight, which is 934. And so the acceleration is 1100 minus 934 divided by 95.3. is 1.742 meters per second squared. Okay, what about when the scale reads 688? That's okay. So we just do the same thing. Acceleration when the scale reads 688 newtons. So I have to write two equations to find net force. I set both of them equal to each other. One of them is that net force equals the mass times the acceleration. That's Newton's second law. The other one is that the net force in the direction of motion is the normal force exerted by the floor minus the gravitational force exerted by the earth. I set those equal. They both equal net force. So net force is mass acceleration, but it also equals normal force minus the gravitational force. Again, I'm solving for the acceleration. The difference here is that now the normal force is no longer 1100. Now it's 688. His weight is still 934 newtons. That hasn't changed. His mass is still 95.3 kilograms. Okay, so the acceleration is going to be 688 minus 934 divided by 95.3. Oh, look, it's going to be negative. 688 minus 934, right, is negative 246. But then I divide by 95.3. His acceleration is negative 2.581 meters per second squared.